All right, hello and welcome back to the Calculus video lecture series. Today we are going to be switching gears completely and looking at something called antiderivatives and the indefinite integral. So, what an antiderivative is exactly what it sounds like. Antiderivatives are basically derivatives backwards. So if you have a function capital F is the antiderivative of f if the derivative of capital F equals f of x. So basically, antiderivatives are the opposite of derivatives. So there's going to be formal notation for this in just a second, but when you are finding the antiderivative of, let's say, 2x, what you are asking yourself is what function gives me a derivative of 2x. So, what function gives me a derivative of 2x? Well, that's x squared. Now, can you think of a different function that maybe has the same derivative? So yes, the derivative of x squared is 2x, but so is the derivative of x squared plus 5. Derivative of x squared plus 5 is still 2x. The derivative of x squared minus 3 is also 2x. The derivative of x squared minus 10.75 is also 2x. So here's how antiderivatives are very different from regular derivatives. A derivative of a function is a definite exact function, whereas antiderivatives are more of a family of functions. So the antiderivative is all of the antiderivatives of f of x. So the antiderivative of of 2x was x squared plus some arbitrary constant c. So this is how we will represent the antiderivative. So the antiderivative of 2x is any function of the form x squared plus some arbitrary constant c. So x squared plus any arbitrary constant c will all have the same derivative. So that's the thing with antiderivatives, is they are a family of functions all of the same form, and they only differ by that constant plus c. So every single antiderivative does need a plus c on it because you have to account for the fact that any function, the derivative of any constant is going to be 0. Again, I'm going to give you formal notation for this in just a moment, but we're going to find the antiderivatives of each of these functions. So starting with the antiderivative of cosine. So you have to ask yourself, what function gives me a derivative of cosine? Well, the sine will give me a derivative of cosine. So sine x is going to be the derivative of so the derivative of sine x is going to give me cosine. So the antiderivative of cosine is going to be sine x plus any arbitrary constant c. So the derivative of sine x plus 5 will give me cosine x. The derivative of sine x minus 100 will give me cosine x. So the antiderivative of cosine x will be sine x plus any arbitrary constant c. So this is what is meant by a family of functions. Sine x plus any constant will give you a derivative of cosine. Now for this next one, I will say that antiderivatives will share a couple of the same rules as derivatives. One of them is the sum and difference rule. So we're just going to take the antiderivative of 1 over x plus 2e to the 2x one at a time. So for 1 over x, what you have to ask yourself is, okay, what function gives me a derivative of 1 over x? Well, that's the natural log of x. Then for the next term, you have to think chain rule backwards. What function gives me a derivative of 2e to the 2x? Well, the function that gives me a derivative of 2e to the 2x is e to the 2x. So natural log x plus e to the 2x plus any arbitrary constant c will give me the same derivative. So this is going to be the antiderivative of our function f of x. Now, antiderivatives are also known as indefinite integrals. So going back to derivatives for a second with Leibniz's notation, you might remember that d dx of f means take the derivative of the function f with respect to x. Now, there is a specific notation that means take the antiderivative of f with respect to x. So the general antiderivative is also known as the indefinite integral, and it looks something like this. So we're going to get to where this notation comes from historically. We're going to get to that a little bit later once we have a little bit more background information. But for now, this right here, this kind of elongated S-looking thing is called the integral symbol. So this means this is called an integral, and it just means at this point take the antiderivative of the function f of x. And this dx here is actually important because this dx tells you what variable you are integrating with respect to. This is also called the variable of integration. So in this case, here's how we're going to read this. We're going to take the indefinite integral of f of x with respect to x. That's what the dx means. We're integrating with respect to that independent variable x. And then the indefinite integral is just the formal notation for take the antiderivative. So we're going to do that same thing for this next one. So the integral of 3x squared dx means we are taking the antiderivative of 3x squared with respect to x. So what we're going to ask ourselves is, okay, what function gives me a derivative of 3x squared? Well, the function that gives me a derivative of 3x squared is going to be x cubed. And then plus any arbitrary constant c will give me all of the same derivatives. So this indefinite integral is equal to x cubed plus c. Indefinite integrals, antiderivatives always need a plus c because the derivative of any constant is 0. So antiderivatives or indefinite integrals are families of functions. You have to have the plus c here. So then for this next one, for the integral of 1 over 1 plus x squared dx, we're going to do basically the same thing. What this is asking is, okay, what function gives me a derivative of 1 over 1 plus x squared? And I will give you the hint that this is on your derivative rule sheets. This is actually tan inverse. The derivative of tan inverse is 1 over 1 plus x squared. So the integral of 1 over 1 plus x squared is the tan inverse of x plus any arbitrary constant c. So then for this last one, for the integral of sine x with respect to x, we are asking ourselves, what function gives me a derivative of positive sine x? Well, the function that will give me a derivative of positive sine x is actually going to be negative cosine x plus any arbitrary constant c. Now, like I said, antiderivatives do have a couple of rules in common with derivatives, so here are a couple of them. So if you have a constant multiple inside of an integral, you can take it out and write it as multiplication outside of that integral. This is actually going to come in more handy than you think because there are going to be instances where you have a constant that's just kind of getting in the way of you being able to use one of your integral rules that I'm going to give you in a little bit. Now, this sum rule is also applied to a difference, so if you have addition or subtraction inside of an integral, you can simply take the integral of each part and then add and subtract them together. So you can split it up into the sum or difference of two separate integrals. You can also think of this as if you have addition or subtraction in your integral, you can simply integrate one term at a time. Now, just like there is a power rule for derivatives, there is a power rule for integrals. So I'm going to refresh your memory on the power rule for derivatives. Give me 1 second to fix whatever this is. Okay, I think we're back in business. So just like there is a power rule for derivatives, there is also a power rule for integrals. So I'm just going to refresh your memory on the power rule for derivatives. So for example, if you have x to the power 4, the power rule for derivatives means that you move down the power, and when you move down the power, you write it as multiplication, and then you decrease the power by 1, so you subtract 1. Because antiderivatives are derivatives backwards, there is a power rule for integrals, and it is the exact opposite. So for the power rule for integrals, instead of decreasing the power by 1, we are going to increase the power by 1. And instead of multiplying, we are going to divide by that new power, and then don't forget the plus c. So that's generally what we're going to do. Anytime we're taking the integral of x to a certain numeric power, we're going to increase the power by 1, and we are going to divide by the new power. Now, the only power that this does not work on is -1, because x to the power of -1 is actually 1 over x, which has its own integral. So the integral of 1 over x is actually natural log of x. So -1 is the only numeric power that power rule for integrals does not work on. So power rule for integrals is going to work on every single other exponent besides -1. Okay. Now keep in mind, this is actually really important. There is no product rule for integrals, and there is no quotient rule for integrals. Products and quotients inside of an integral are handled on a case-by-case basis. We're going to look at a couple of the techniques to handle some products and quotients in this class, and then more techniques to handle products and quotients will be covered in Calculus 2. So keep in mind, there is no product rule for integrals, and there is no quotient rule for integrals. No product rule, no quotient rule. So that means that anytime you see a product or a quotient, you really need to do some rewriting first to get rid of that product or quotient before you integrate. So I'm taking a look at this first integral, and I immediately see a variable in the denominator. Since there is no quotient rule for integrals, I have to rewrite this before I can take any antiderivatives. Luckily, it is an easy fix. So one way to rewrite that x to the 3/2 in the denominator as something that's not in the denominator is to make it negative. So I'm going to turn that into an x to the power of -3/2 and put it back in the numerator. And now there is no quotient, so now I don't have to worry about it. So according to the sum and difference rule for integrals, I can simply integrate one term at a time, and any constant multiples, just like they did with derivatives, are going to stay there. So for the integral of 3x to the 5th, because this 3 is a constant multiple, I'm just going to leave it alone. Then for x to the 5th, I'm going to use the power rule for integrals. So for the power rule for integrals, I'm going to increase the power by 1, and then I'm going to divide by the new power. Then plus, I'm going to do the same thing for the next term. Now technically with this 2, there is an x to the power 0 here. So that constant multiple of 2 is going to stay where it is. And then for x to the power 0, I'm going to increase the power by 1 and divide by the new power. Then for the last term, I'm going to leave the -5 alone because it's a constant multiple. And then I'm going to use the power rule for -3/2. So I'm going to increase the power by 1. So -3/2 plus 1/2 is -1/2. And I'm going to divide by that new power, -1/2. And then don't forget, because this is an integral, a general antiderivative, we're going to add a plus c, because any function in this form plus an arbitrary constant c will give us all the same derivative. And now I'm just going to clean up my constants. So 3 over 6 can simplify to 1/2. X to the 6th. This whole second term can just be reduced to 2x. And then negative times a negative is a positive. 5 divided by 1/2 is 10. X to the power of -1/2 plus c. So then this is going to be your final answer. That is going to be your antiderivative, your family of functions that all give the same derivative. Now for this next one, there is no quotient rule for integrals. Because there's no quotient rule for integrals, do not simply take the integral of the top and the integral of the bottom. Also, don't even try to use the quotient rule for derivatives here. It doesn't work. But if you notice, the denominator here only contains one single term. So what I'm going to do is I'm going to split up that subtraction in the numerator as a subtraction of two separate fractions, all with that same common denominator, x squared. It's basically subtracting fractions with a common denominator in reverse. So I'm going to split this up into 4x to the power of 19 over x squared minus 5x to the power of -8 over x squared dx. Notice, until you're actually ready to integrate, do not drop the integral symbol and do not drop the dx. Also, as you notice back up here, The integral symbol and the dx are a package deal. So as soon as you take the integral, both the integral symbol and the dx both go away at the same time. So they're either both there or they're both not there. Anyway, so let's do a little bit more simplifying so that I don't have a quotient to deal with. I'm going to use the quotient rule for exponents. So remember, if you have x to the power of 19 in the numerator divided by x squared, you can simplify by subtracting the power, so that'll give us 4x to the power of 17. Then minus 5, I'm going to do the same thing here. I'm going to take our top exponent, negative 8, subtract our bottom exponent, negative 2, and that will give us minus 5x to the power of negative 10. So now that we have simplified it so that there are no more quotients, now I can use the power rule for integrals. So this constant multiple of 4, I'm going to leave it alone, and I'm going to use the power rule for x to the 17th. So I'm going to increase the power by 1, x to the power of 18, and I'm going to divide by that new power, 18. Then I'm going to leave that constant multiple of minus 5 alone, and I'm going to do the same thing for the x to the power of negative 10. I'm going to use power rule. So negative 10 plus 1 is negative 9. And then I'm going to divide by that new power, negative 9. And because this is a family of functions, we do need a plus c on the end. And then I'm just going to finish up by cleaning up my constants. So 4 over 10 can be reduced to 2 over 9, x to the power of 18. Negative times a negative is a positive, 5 over 9. X to the power of negative 9 plus c. And then this is going to be your final answer, your final antiderivative. Again, there is no product rule for integrals, and there is no quotient rule for integrals. So because there's no product rule for integrals here, we are going to have to do some distributing first before we integrate. So let's distribute. So x squared times 2x is going to give us 2x cubed, and then minus 5x squared, and then plus 2x minus 5 dx. Notice that if all you're doing is simplifying, I did not drop the integral symbol and I did not drop the dx. Do not drop either the integral symbol or the dx until you are actually ready to integrate. All right, so from here, I'm going to use the power rule for integrals one term at a time. So I'm going to leave the constant multiple of 2 where it is, and I'm going to increase the power by 1 and divide by that new power 4. Then I'm going to leave the constant multiple of minus 5 alone, and I'm going to increase the power by 1, gives us x to the 3rd, and I'm going to divide by that new power 3. Then remember, this is a 2x to the power 1, so I'm going to leave that constant multiple of 2 alone. I'm going to increase the power by 1, gives us x squared, and I'm going to divide by that new power 2. Then for the integral of minus 5, like we saw in the last example, that will give us minus 5x when we increase the power by 1 and divide by the new power. Then, because this is an indefinite integral or an antiderivative, we do need an arbitrary constant plus c. So then let's just tidy up the constants. 2 over 4 can reduce to 1/2, x to the 4th, and then minus 5/3, x to the power 3. And then, 2 over 2 can cancel out, giving us plus x squared, and then minus 5x plus c. And then that is going to be our antiderivative. So then for this last one, this is, you're going to see stuff like this a lot. Because for reasons we're going to find out later, the dx is technically being multiplied. So if you have a fraction and the numerator is just 1, a lot of times the dx is just brought into the numerator of this fraction. So if you really don't like the way this is written, you can easily rewrite this as 1 over 3 times the cube root of x dx. That's really all it was. The dx just drifted into the numerator because the numerator was just 1. So then again, there is no quotient rule for integrals, so I'm going to have to rewrite this. And while I'm at it, I'm also going to rewrite that cube root of x as an exponent. So the cube root written as an exponent is 1/3, and because it's in the denominator, I'm going to get it out of the denominator by writing it as x to the power of negative 1/3. Now that 1 over 3 can be written as a constant multiple of 1/3 dx. So now that we have it written in a form that we can work with, we're going to use the power rule to integrate. So we're going to leave that constant multiple of 1/3 where it is. I'm going to increase the power by 1. Negative 1/3 plus 3/3 is 2/3. And then dividing by 2/3 is the same as multiplying by 3/2. Then, because this is a family of functions, don't forget the plus c. And then when you simplify this, 1/3 times 3/2 is 1/2, x to the power of 2/3 plus c, and then that is going to be your final answer. Now, those derivative rules sheets, all of those derivative rules, if you do them backwards, become integral rules. So if you have the integral of cosine, you get sine because the derivative of sine is cosine. Now, thinking in terms of chain rule, remember, anytime that you are taking the cosine or sine of anything other than just x, if you were taking derivatives, you would need to use the chain rule. So we're basically going to be using chain rule backwards for this. So if you have the integral of cosine of some number a times x, that is going to be 1/a times the sine of ax. And then same thing for the integral of sine of ax. If you're taking the integral of sine of ax, that's going to be negative 1/a cosine of ax plus c. And then this is another important one, tangent. So the integral of secant squared of ax is going to equal 1/a times the tangent of a plus c. So if you're taking a look at the integral of secant squared of 3x, what you're essentially asking yourself is, what function gives me a derivative of secant squared? Well, the derivative of tangent is secant squared. Now, since this is the secant squared of 3x, you do have to think chain rule backwards. So the integral of secant squared of 3x is actually going to be 1/3 times the tangent of 3x plus c. Then for this next one, for the cosine of x/2, remember you can think of that x/2 as 1/2 x. So what you have to ask yourself is, what function gives me a derivative of cosine? Well, the function that gives me the derivative of cosine is going to be sine. So the integral of cosine of 1/2 x is going to be the sine of 1/2 x, or x/2, times 1/1/2, which is just 2, plus c. And then for this last one, we're going to integrate one term at a time. So we're going to take the integral of 2x. So the integral of 2x is going to be x squared. Then we're going to leave that constant multiple of 3 where it is. And we're going to take the integral of cosine. So for the integral of cosine, you are asking yourself, what function gives me a derivative of cosine, which is sine? So 3 sine x. And then, like with any other indefinite integral, because this is a family of functions, you do need a plus c. Now remember, all of those derivative rules, if you do them backwards, now become integral rules. So just like the derivative of e to the x was itself, the integral of e to the x is itself. So if you're taking the integral of e to the ax, it's going to be 1/a times e to the ax plus c. And then here's another important one. So the integral of 1/x, or dx over x as it's very commonly written, is going to be the natural log of technically the absolute value of x plus c, although it's not a huge deal if you don't have the absolute value there. Because remember, -1 is the only power that power rule for integrals does not work on, because the integral of 1/x is going to be the natural log of x. And then the inverse trig functions, you are also going to be responsible for. So for example, if you have 1, or dx, over the square root of a squared minus x squared, that is going to be the sine inverse of x over a plus c. And then another one, if 1/1 plus x squared, or dx over a squared plus x squared, is going to be 1/a times the tan inverse of x over a plus c. Now just keep in mind, especially with these two, in order to use these two integral rules, your integral needs to be set up in the exact same way that these rules are set up. Integrals, unlike derivatives, are extremely delicate. If your integral does not look exactly like 1 over square root of a squared minus x squared, you cannot use this integral rule. And if your integral does not look exactly like 1 over a squared plus x squared, you cannot use this integral rule for tan inverse. Also keep in mind, because there's no quotient rule for integrals, anytime that you see a quotient, you do have to think of trying to do some rewriting so that there is no more quotient, so that you can actually take its integral using power rule. So I'm going to have to do some rewriting first before I integrate. Now, while you are rewriting, don't forget that you do not drop the integral symbol and you do not drop the dx. So since the denominator just has this one single term, I am going to split up the addition in the numerator into the addition of two separate fractions, all with the same common denominator. And while I'm at it, I'm also going to rewrite that square root as an exponent of 1/2. So that will give me x over x to the power of 1/2 plus 1 over x to the power of 1/2 dx. So then what I'm going to do is I'm going to use some basic exponent rules to simplify. So x to the power 1 divided by x to the power of 1/2. I'm going to subtract the powers, gives me x to the power of 1/2. Then I'm going to rewrite 1 over x to the power of 1/2 so that it's no longer a quotient, gives us x to the power of negative 1/2 dx. So now that I've got this rewritten in a form that I can work with, I am going to use my power rule to take this integral one term at a time. So I'm going to increase the power by 1, so 1/2 plus 1 is going to give us 3/2. Then I'm going to divide by that new power. Dividing by 3/2 is the same as multiplying by 2/3. Plus, I'm going to do the same thing for the next term. I'm going to increase the power by 1, gives me x to the power of positive 1/2. Then dividing by 1/2 is the same as multiplying by 2. Then, because this is a family of functions, you do need a plus c, and that is going to be your final answer, your final family of functions. Now for each of these, we are going to be thinking of using the same derivative and integral rules as a couple slides ago. So for the integral of e to the negative 10x, remember that the derivative of e to the x is itself, but as soon as you take the derivative of e to anything other than just x, you will need chain rule. So we're basically going to think chain rule backwards for this. We're asking ourselves, what function gave me a derivative of e to the power of negative 10x, which is negative 1 over 10, e to the power of negative 10x. And then, because this is a family of functions, you do need a plus c. Now this next one is an example of a constant multiple that is getting in the way. If you take a quick look at this, it does look at first glance like this should be a sine inverse. However, the derivative of sine inverse only has a 1 in the numerator. So remember, any constant multiple that is inside of an integral can simply come out of the integral and be rewritten as multiplication. So I'm going to take that 4 out of the numerator and I'm going to write it in front as multiplication. And that will give me 1 over, now 9 is going to be 3 squared, so I'm just going to rewrite 9 as 3 squared minus x squared dx. So then if you take a look at this, this looks exactly like sine inverse. This looks exactly like this rule here. So the antiderivative is going to be sine inverse of x over a plus c, and a in this case is 3. So we're going to get 4 times the sine inverse of x over 3 plus c. Now for this next one, remember the only power that power rule does not work on is negative 1. So what you have to ask yourself for this is, what function gives me a derivative of 1 over x? Well, that is the natural log of x, so the integral of 1 over x dx is going to be natural log of x plus c. And then for this last one, remember there is no quotient rule for integrals, so I'm going to rewrite that 3 in the denominator as a constant multiple of 1/3 e to the x dx. So then the constant multiple is just going to stay there like it did with derivatives, and the integral of e to the x is itself, so I have 1/3 e to the x plus c is my final answer, my final antiderivative. So then for this next one, if you take a look at this, you might notice that it looks very similar to tan inverse, but it's not exactly the same. So for tan inverse of x, it would have to be 1 over a squared plus just x squared. So what we have to do here is we can do some little bit of rewriting so that we turn this into 1 over something squared plus just x squared. And the way that we are going to do that is we are going to kind of force a GCF where there isn't one. So in the denominator, I am going to force there to be a common factor of 16 that I'm going to force factor out of both terms. Remember, when you factor out a constant, you simply divide each term by that constant. So 16x squared divided by 16 is 1x squared, plus 1 divided by 16 is 1 over 16. Now this 16 in the denominator can be written as a constant multiple of 1 over 16, which I'm also just going to take out of the integral entirely so that I don't have to worry about it. Then inside the integral we have dx over x squared plus 1 over 16 is actually a perfect squared. 1 over 16 is actually 1/4 squared. So now if you take a look at this integral, dx over x squared plus 1/4 squared, it does look exactly like the integral rule for tan inverse right here. And it doesn't matter if those are switched. So the integral is going to be 1 over a tan inverse of x over a, where 1/4 is playing the role of a. So my integral is going to be, I'm going to leave that 1 over 16 where it was, times 1 over a, 1/4, times the tan inverse of x over a, so x over 1/4, plus c. And don't leave it like this, please. So we're going to just clean up these constants a little bit. So first of all, 1 over 1/4 can be simplified as 4. 4 times 16 is going to give us 1/4. Tan inverse of x over 1/4 can be simplified as 4x plus c. And that looks a lot better. So then for this next one, again, this is one of those instances where we do have a couple of constants that are kind of getting in the way. And also, if you want to, you can split this up into the subtraction of two separate integrals. So I'm actually going to split this up into the subtraction of two separate integrals so that you can see each integral rule at work individually. So I'm going to split this up into the integral of 4 over 3 square root of 1 minus x squared dx minus the integral of 3 over x dx. Then we got a couple constant multiples that are getting in the way of using our integral rules because, that first one looks really similar to sine inverse and that second one looks almost exactly like natural log of x. So I'm going to take this constant multiple of 4/3 and I'm going to write it outside of the integral. So I have 4/3 times 1 over the square root of 1 minus x squared dx. Then I'm going to do the same thing over here. I'm going to take this constant multiple of 3 and I'm going to write it outside the integral, giving us 3 times the integral of 1 over x dx. Now for that first one, that 1 over square root of 1 minus x squared, looks exactly like this, where a in this case is 1, so that is going to be sine inverse. So I'm going to leave the constant multiple of 4/3 where it is. The integral of 1 over square root of 1 minus x squared is going to be sine inverse. And then minus 3, integral of 1 over x is going to give us natural log of x plus c. You only really need one constant, one arbitrary constant. So just 1 plus c on the end will be more than sufficient. So our final answer, we get 4/3 sine inverse of x minus 3 natural log of x plus c. There are going to be a lot of applications of integrals. We will do some applications of integrals in this class, and then you are going to do a ton of others in Calculus 2. And remember, your major courses that require calculus are also going to have applications of both derivatives and integrals that are unique to your specific degree program. But one of the main applications of integrals or antiderivatives is in what is called differential equations. In simple terms, a differential equation is any equation that contains a derivative. So a differential equation is in the format like this. We have some derivative dy dx equals some other function f of x. So to solve something like this, you would need to undo the derivative. The opposite of a derivative is an antiderivative. So the solution to a differential equation involves finding the function that gives you this given derivative. So in other words, solving a differential equation is going to involve you finding antiderivatives or indefinite integrals. Now, with differential equations, we actually have two different types of solutions. Because remember, when you just take an antiderivative, you always have a plus c. You always need that arbitrary constant because just a general antiderivative is a family of functions. So when you take the general antiderivative of your differential equation, you're going to get a plus c at first. That is what is called your general solution. And a general solution is a family of functions that all would satisfy the same equation. Now, in order to actually get a specific function, not just something with a plus c, not just a family of functions, you will need what is called an initial condition. An initial condition is just some extra information about the problem, about the original equation, that will allow you to solve for c. So what you do is you take your general solution and you plug in what is called your initial condition. When you plug in your initial condition, that will allow you to actually solve the equation for c. Then when you plug c back into your general solution, you get what is called a particular solution. And the particular solution is a specific function without a plus c that gives that same derivative and meets that initial condition. So the particular solution is just one function, not a family of functions. So one major application of this is going to be one-dimensional motion. So you might remember that the derivative of position is velocity, and the derivative of velocity is acceleration. So working backwards, if you know an object's acceleration, you can integrate it to find the object's velocity, because the antiderivative of acceleration will be velocity. Now, if you know the object's velocity, you can integrate it to find the object's position, because the antiderivative of velocity will be position. So for this first one, let's say that runner A begins at point s of 0 equals 0 and runs with velocity function v of t equals 2t, where t is measured in minutes. Now runner B is going to begin with a head start at the point s of 0 equals 8 and run with velocity function v of t equals 2. So what we're going to do is we're going to use integrals to find the position functions of both runners and use those position functions to figure out who is ahead at 6 minutes. So since we have two separate runners, we're going to basically have two separate differential equations. Let's start with runner A. So runner A runs with the velocity function v of t equals 2t. Now, an integral, just like a derivative, is an operation. So whatever you do to one side of an equation, you need to do the exact same thing to the other. So what I'm going to do with this is I am going to integrate both sides with respect to t. You always integrate with respect to the independent variable. So in this case, since the independent variable is t, we're going to take the integral with respect to t. So I'm going to take the integral of v of t dt, and that is going to be the integral of 2t dt. Whatever you do to one side of an equal sign, you need to do to the other. So the integral of velocity is position, which, because there's going to be two position functions, I'm just going to denote this as s of a. So, sa of t is just going to be the position function for runner A, and that is going to equal, give me a moment. So that is going to give us the position function for runner A equals the integral of 2t with respect to t. What function gives me a derivative of 2t? That is going to be t squared plus c. Remember, just a general antiderivative will give you a family of functions, and this is called the general solution. To actually figure out what c is, and get the actual position function for this specific runner, we're going to use the initial condition given for runner A. So runner A began at the point s of 0 equals 0. So I am going to plug 0 in for t and 0 in for s of t, and I'm going to solve for c. So I have 0 equals 0 squared plus c, giving us c equals 0. Now the whole point of solving for c is so that you can plug 0 back into your general solution in for c, and when you plug 0 back in for c in your general solution, you are going to get your particular solution. So the position function for runner A is going to equal t squared. So because there is no more plus c, this is our particular solution. So then we're going to do the same thing for runner B. So runner B has a velocity function of v of t equals 2. So to find the position function, I am going to integrate the velocity function. So I am going to take the integral of both sides with respect to t. So the integral of v of t dt is going to equal the integral of 2 dt. So the integral of velocity is called position, so I'm going to call this position function sb of t, equals, for the integral of 2, what function gives me a derivative of 2? That is going to be 2t plus c. So this, again, is what is called the general solution for runner B. To find the particular solution for runner B, we're going to plug in the initial condition that we are given for runner B. So I'm going to plug 0 in for t, and 8 in for s of t, and I'm going to solve for c. So in for s of t, I'm going to plug in 8. Then in for t, I'm going to plug in 0. And then I'm going to solve for c, and that will give us c equals 8. So once you have solved for c, don't forget to plug 8 back into the general solution in for c to get your particular solution. So your particular solution will be the position function for runner B, which is 2t plus 8. So now that we have position functions for both runners, we can easily figure out who is ahead at 6 minutes by just taking each function and plugging 6 in for t. So if you take the position function for runner A and you plug in 6, you get 36. And then if you take the position function for runner B and you plug in excuse me, and you plug in 6, you are going to get 20. So obviously A is ahead. So because the position function for A was greater than the position function for B at 6, A is ahead at 6 minutes. So for this next one, let's say that a balloon is rising at a rate of 12 feet per second with a velocity of 40 meters per second from the edge. Oh, hold on, give me a second. So yes, so let's say that a stone is thrown vertically upward at t equals 0 with a velocity of 40 meters per second from the edge of a cliff that is 100 meters above the river. Because this is calculus 1, we are going to neglect air resistance. Neglecting air resistance, the acceleration due to gravity is 9.8 meters per second squared. So what we're going to do is we're just going to use this little bits of information to find both the velocity function and the position function. So let's start with part A, the velocity function. So the acceleration function. Now keep in mind, gravity always pulls down. So because gravity is a force that always pulls down, the acceleration function is actually going to be a negative 9.8 because, gravity pulling down is why the stone goes down. So the acceleration function is negative 9.8. Now because the derivative of velocity is acceleration, that means the integral of acceleration is velocity. So what I'm going to do with this is I am going to take the integral with respect to t of both sides of this equation, and that will allow me to start finding the velocity function. So integral of acceleration, that is called velocity, v of t, equals the integral of negative 9.8 with respect to t is negative 9.8t plus your arbitrary constant c. So remember, this is what is called your general solution for velocity. To get the particular solution for velocity, you do need an initial condition. So the initial velocity was that 40 meters per second, so your initial condition is v of 0 equals 40. The velocity at time t equals 0 equals 40. So what I'm going to do is I'm going to plug 40 in for v of t and 0 in for t, and I'm going to solve for c. So that'll give us 40 equals negative 9.8 times 0 plus c. And then when we solve for c, we get 40. Now remember, the whole point of solving for c is to get your particular solution, so don't forget to take 40 and plug it back into the general solution in for c to get your particular solution. So v of t is going to equal negative 9.8t plus 40. And then that is going to be your velocity function, your particular solution. Now for part B, to find the position function, because the derivative of position is velocity, that means the integral of velocity will be position. So to find the position function, I am going to take my velocity function, and I am going to take the integral with respect to t of both sides. So I have the integral of v of t dt is going to equal the integral of negative 9.8t plus 40 dt. So the integral of velocity, that is called position, s of t, equals, now for negative 9.8t, we're going to use the power rule. So we're going to leave the negative 9.8 alone. We are going to increase the power by 1 and divide by the new power. Plus integral of 40 with respect to t will be 40t. And then don't forget we have our plus arbitrary constant c. So negative 9.8 divided by 2 will give us negative 4.9. So we have s of t equals negative 4.9 t squared plus 40t plus c. Now remember, this is what is called your general solution for this differential equation. To find the particular solution, we do need an initial condition for position. So it was tossed from a cliff that is 100 meters above the river, so the initial position is 100. So s of 0, position at time t equals 0, equals 100. So what I'm going to do is I'm going to plug 0 in for t and 100 in for s of t, and I'm going to solve for c. So I get 100 equals negative 4.9 times 0 squared plus 40 times 0 plus c. And then when we solve for c, we get c equals 100. Now don't forget to plug this 100 back into your general solution in for c to get your particular solution. So your particular solution, the position function, is going to be negative 4.9 t squared plus 40t plus 100. So plus 100. And that is your position function. So we are going to be using antiderivatives a lot more. The entirety of Chapter 5 is actually going to be devoted to integrals and the other type of integral, which is called the definite integral, which we will get to in a little bit. So keep in mind that this entire chapter is going to involve integrals, and we will be taking antiderivatives a lot. So make sure that you do your antiderivatives homework before you tackle the rest of the chapter, because you're going to be using a lot of these same techniques throughout this chapter. We are going to do some integral rules in this class, and then in Calculus 2 you are going to cover the rest of the integral rules. The first half of Calculus 2 is going to be basically devoted to integration techniques. So thank you all very much for watching, and I will see you all in the next video.